This lecture is about the binomial tree models, covering Jiang Ho's book, Chapter 12 and Chapter 18. Binomial trees are approximation method, which is frequently used to price stock options. You divide the time into small intervals. In each small interval, the stock price will assuming to be moved either up or down. Now let's do some simple examples from chapter 12. We're starting from one step, looking at two step, and then three step. Any multiple spread in the future, particularly in chapter 12, chapter 18, you can use Jiang Ho's derived gene, the software, to do it. Let's look at a simple binomial model, one step. The stock price currently is traded at $20. Let's suppose in 3 months, it will either jump to $22 or drop to $18. In other words, they're like 10% up or 10% down. So the up movement is 1.1, and the down movement factor here is 0.9. So this is what the stock will look like, either $22 or $18. Now let's look at an option is written on this stock. Let's assuming this is a 3-month call option. Has a strike price of $21. Now let's put the option price or option value underneath the stock price. Let's look at the back, the very end of the 3 month. If stock price is $22, the option price will be 22 minus 21 equal to $1. It'll be in the money, worth $1. Now, if the stock goes down to $18, this call will be out of money. Now, our question is, what is the option price you pay now? Here is the question mark. What the price you pay now? Now, let's assuming we can set up a risk-free portfolio, which basically perfectly hedged. So no matter what happened, either up or down, you have the same return. Consider the following portfolios. If you long delta shares of the stock, the delta means number of shares, assuming, for example, 0.5, right? Half share, 0.5 shares. But short one call option. In other words, you have portfolio. Within the portfolio, you have half share of stock, but a short position in one call. Now let's look at what happens at the end of 3 months. So if it's upstate, so it will be $22 times the delta. The delta here is the number of shares. For example, is 0.5. Minus 1. Why is minus? Because you are taking a short position. People will exercise against you, so you lose $1. On the other hand, if the market goes down to $18, in that case, the call is out of money. You are safe. But on the other hand, the share price is $18. So 18 times, for example, 0.5. You have $9 is your stock worth. Now here you have two outcomes, but one variables is the delta. Delta here actually is the hedge ratio. Now let's make these two outcomes equal. That means risk-free equal. So 22 times delta minus 1, the up state, or the down state, 18 times delta equal, and solve for the single variable delta. Here the delta equal to 0.25. In other words, a quarter of share of stock. In other words, you long a quarter of share match a short position in a call. You have a perfect hedge. No matter what happens, go up, go down, they give you the same answer. Now, the value of this risk-free portfolio in 3 months will be $4.50, no matter what. If you can plug that in, because delta here, 0.25, is the perfect hedge. Therefore, if you want to know the portfolio today, how much worth, is the 4.5, the risk-free outcome, discounted back by 12%, that's assuming the risk-free rate 12%, for 3 months, 0.25 3 months, which is equal to today's dollar, the present value, $4.3670. This is the portfolio current value. Its future value is 4.5. The current value is 4.37. Okay? Now, let's look at what the portfolio inside which is worth 4.36. The value of the share, since currently it's traded at $20, but you bought only a quarter of it, so you paid $5 for that. Now, $5, which is your is the investment in the equity part, minus the total value of the share, which is the slack for the value of the call option, which is 0.633. Here to show you, we can, using the no arbitrage argument, to back out the option price. The option price, 0.633. Here, you might say 0.633, 63 cents. Now let's generalize the binomial model in a one step, the simplest one step. Okay, we're using S to represent stock price, F to represent the option. F can be call, can be put. So you see the F will go up times U. S times U is the up factor. Or S will go down. S times the D down factor. So first you're looking at, you map out the path of the underlying stocks. Then we go backwards. If it's upstate, what the core value is. If it's the downstate, what the core value is. Then we discount these two back to today and find what is the today's value. This is the basic essence of the binomial tree model. Now, to the delta ratio is basically is the core value. If it's a call option, I'm using call. You can also use put. Call up minus call down divided by the ratio divided by the stock up and down. So it's the model. So you basically here just showed you algebra, what is the value the call should be in it. Here you can go back to looking for the probability go up, which is equal to the e to the power of RT, which is the risk-free rate go up, minus d, the down factor, divided by the distance between the up factor minus the down factor. which will give you the probability I'll go up. Then 1 minus P, which is the probability go down. So P here is the probability. Here is the probability. Now you have this equation. Looking at a graphic looking wise, is you will say the stock go up at the probability. That level, you get a SU start or go down at a 1 point P. You have a probability for the stock go up or for the call in the money, and probability stock for the call out of money. Then you have almost all the input you needed to calculate its present value. It is basically weighted average expected value. However, here is a key element, is what we call risk neutral valuation. In corporate finance and investment, we know that when you discount the future cash flow, you have to choose an appropriate discount rate. That discount rate will be subject to person's risk preference. Means if you risk averse, then you demand a huge discount rate. If you risk less risk averse, you demand a less risk rate. So each person has its own utility function. Therefore, the discount rate, it becomes a hard to determine what the appropriate discount rate is. But here, the argument, as a matter of fact, initially suggested by Black-Scholes, is using risk neutral, because you take away the expected value. If you remember when we studied Black-Scholes model, out of the equation, you can build up a instantaneously risk-free portfolio. Then no matter what investors' risk preference, they will trade as if it is risk neutral. In a risk neutral environment, the discount rate is a risk-free rate. So the risk-free rate will be much easier. We can using just T-bill rate, right? You can plug that in to calculate for the present value. And that solves a big hurdle in the investment theory about what is the appropriate discount rate you should use. Here we're just using risk-free rate as if it is no risk. As if it's no risk. The one-step binomial tree showed you the general result, assuming you can make the payoff exactly equal no matter it's up and down. Okay? For that kind of return, a risk-free rate is appropriate because there's no risk. And in Black-Scholes model, we also showed that the stocks itself, expected rate of return is irrelevant because it's not in the equation. So here is a numeric example we did earlier. This time, we're going to use the probability we just know we do that. We're using the formula to do the probability. So the probability is equal to, in the numerator, is e to the power of RT minus D, then divided by 1.1 minus 0.9. The probability is 65.23%. Go up, percent go down. Now you plug those things in for 22 times probability 0.6523 plus 18 times 0.34.77 is downside. Now, the whole thing need to be discounted by the risk-free rate 12% for 3 months. And your evaluation, the F here, right? Because you're basically looking at is the up probability times 1 for the call in the money, the downside probability times 0, and you discount the whole thing back. The F value today, right, is 0.633. This is the one-step example. Show you how the binomial tree call option is evaluated. Remember, you're using risk-neutral valuation formula using risk-free rate. Okay. Now let's do a two steps. You think, oh, one step is too simplistic. Let's just gradually increase the step. Let's do a two-step example. Here is a 6 months options on a stock. The example is on figure 12.3 on page 275. First, let's calculate the map for the stock. The underlying stock currently traded at $20, increase 10%, decrease 10%. So increase 10%. Another 20% for 3 months, 24.2. But if go up, then go down, go to 19.8. Now, if it's go down, if two step down, you get a 16.2. So each time step, here we have two steps, one step, two steps, 3 months. The delta T is 3 months, which is 0.25 in terms of year. But the whole horizon is 6 months in terms of T equal to 0.5. So you have a forward-looking map of the underlying stock. Now let's do the exercise. Same exercise option, but for 6 months. Let's assuming it is a European option. What that means is you cannot exercise earlier. You have to be exercised at the very end. Now this time we're going to calculate is from backwards. We're looking at 6 months from now. If the stock is up and up, so we have the node here is the D node, up. So it is stock price 24.2 minus 21. The profit you gain from in the money is $3.20. Right? Now, if it's go up and go down, the stock price at the level of 19.8, you're out of money. If it go down, is out of money, so 0, 0. So looking at the very end, 6 months from now, let's look at back. Let's look at the node of B, which is 3 months from now. Now, since it's a European option, so you have to wait until two things happen, either go up or go down. So it's go up 3.2, go down 0. What is the value at the node B? Now, how to calculate? Is the probability 0.6523 going up times 3.2 plus 0 and discounted back by the interval here. The time interval is 3 months, is equal to 2.0257. So this is the value for if stock go up, the value, one step, the value of the call. Now let's look at if the stock go down, what the value of the call. Now if the stock go down to 18, then this core value at that state is out of money. They are all both 0, so it will be 0. Now you have the interim result of B and C. Now let's calculate the node of A, which is current value of that stock. 2 steps, right? The value at A is the probability of up 2.0257 plus probability go down times 0 and discounted back by 12% for 3 months, which is equal to 1.2823. That is the value for the call today. Now, you find there is a very repetitious, the calculation is very repetitious. probability go up, probability go down. And also including what we call the discount factors. The e to the power of negative 0.12 times 0.25. That one is actually a discount factor for 3 months. So here they showed you a call option in 2 steps for 6 months. So each step, each time step should be the same. The interval should be same. So you can enlarge that for a European call. Now here, let's look at the put option. Now this put option is starting from $50, the stock from $50, then go to 60, going to 72, right? Then going down, going up. So let's look at how that be done. 20%. Why is that up on 1.32? I need to check this number. But anyway, so first you calculate 50, 60, and 72. Sorry, this is European. 72. Then going down 40, going up 48, then going down 32. So first you're mapping out the 2-year, or here is the 2-year stock price. Then we calculate backwards. From 2 years from now, exercise 52 is a put option. Put option is the K52 minus ST. Here 72 is a negative, so it's 0, out of money. 52 minus 48, so in the money, $4. 52 minus 32, $20 in the money. What is next? Next, you calculate the interim value for the put. B, the note B, is the probability times 0 plus 1 minus probability go down times 4, discounted back by 5% for 1 year. You get a 1.4147. Also calculate C, same logic, going up, going down with probability 0.6282 according to the formula. Finally, you're looking at, since it's European option, and you're just looking at let it go further one step, what the value is, what the present value is. And using those present value become future value, calculate another present value today, which is worth 4.1923. So this is the value for put today. You first go forward, then go backwards, find the option price. Now, in a European option, you are not allowed to be exercised earlier. But if it's an American option, you can exercise earlier. The textbook show you the input option. There is some situation you should exercise early. This is my next example. Everything's the same. The only thing is the payoff for the this put option is an American. The American feature actually is early exercise. So let's look at the B here. Look at B here. Same thing. Go up, go down with the value, this option, this put option, at time up a year from now, Wednesday is up. It worth 1.4147 if it's alive. However, we also have to check if you kill the option or exercise earlier a year from now, when it's 60. So you will not exercise because it's 52 is the exercise price. So it's out of money, so you will not exercise. Rationally, you will wait for 1 year, right? Now let's look at if it's down. If it's down, let's look at what the value is. You find out the value from $4 and then $12 as a payoff, discounted back 1 year from this two, go back to C, it's worth 9.4636. Earlier we have the example, see? 9.4636. But however, this is the American option. I can exercise immediately. So if hit 40, this put in the money. 52 exercise price, 52 minus 40 equal to 12. So the early exercise give you $12, but if you wait, let the put alive to be one more year, is 9.46. You kill it earlier. So you using the $12, which is early exercise, as C value, not the 9.46, the alive value. Now the future payoff for this American option are either 1.41 or 12. We using the same probability, going up, going down, looking at the present value today, which is 5.0894. Compare this one with the previous one, 4.19 European option. This one is high. Why? Because you can kill it earlier, as if you have like a 20/20 hindsight. Okay, so you can get like a American option in most cases, at least the same price like European, but sometimes it might be higher because it allows you to exercise earlier. Okay. Still using probability neutral valuation. Let me just go directly to the model. I forgot this is from the book or from my own notes, because this is basically is the solution to all the early discussion for multiple the steps. It's what we called CRR model. Now, theoretically, everybody talking about Black-Scholes, Merton. But in reality, a computer programmer, what they do, they're all using CRR model by Cox, Ross, Rubinstein. By the way, Mark Rubinstein is my professor. But they come up with this model. The upslope here, U is the upward factor with e to the power of sigma times square root of delta t. My alarm went off. Okay. U is upwards. Now, let's look at D. D is just inverse of U. You can just write the inverse of U. So the e to the power of negative sigma times square root of dt. Now, what does delta times square root of dt remind you? The geometric Brownian motion, remember, is a function of time. The function time. So here is geometric Brownian motion. So the upward, we're using this formula. Downward, we're using the inverse of upward, the factor in it. Here, the probability by Cox, Ross, Rubinstein is the alpha minus d minus u minus d divided by u minus d. Here, the alpha depends on what option is that. If the option is a stock, the underlying asset is a stock option, the alpha is the risk-free rate times delta t. Delta t is the interval. How long? Like 3 months, 6 months, 1 week, 1 day. But in terms of delta, always in terms of year, okay? For index option, now we have assuming the constant dividend yield at Q. So the alpha, the drift term, the alpha, is e to the power of risk-free rate minus dividend yield, then times delta t. For a currency option, the drift term is equal to exponential equation function times domestic interest rate, risk-free interest rate minus foreign interest rate times delta t. The last one is the futures option. Since the futures option does not require any money, let's ignore the market to market requirement. So the drift term has no drift. is 1. Straightforward. There is no increase growth rate. The future, because you do not hold the cash position, is a future position. The alpha equal to 1. So please make a note on this slides. This is basically summarize all those modeling need for binomial model. You should plug in this model as for P. What the P is depend on what underlying asset you are working at, and the calculation is pretty straightforward. Now, in order to save your time, I'm going to allow you to using the John Ho's model to the binomial model. But in real world, the binomial model will allow you to do the steps, do up to like 500 small steps, 500 small steps. The higher the frequency, the better the result, the more accurate. Let's assuming Black-Scholes give you the exact formula, but the CRR model will give you approximation. Usually you have to like a 30 to 40, even 50 to give you a good value, close. Later I will show you that. The one step, two step, the one step is too rough. This is basically teach you the basic, the mechanic behind it, but you really require at least 30 time steps. We will show you later. Here is example. Oh, this is from 18, not 16. I'm using the old examples here. I forgot what this example. Yeah, 16, I think. First, what you do is go to up, 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 down, down, down. Here's 1, 2, 3, 4. 4 steps. Right? If 4 months, going to 1 month. First, you go upward, then go down. Now, the go down is called the backwards induction. We know the option at the final node. You work backwards through the tree using risk-neutral valuation, risk-free rate, to calculate the value of the option at each interim node. If it's American option, you also test for early exercise value when to check to see which one is higher. Always choosing the high value, then you'll calculate. Here's example. Here example of put option. Put option sometimes you will have to involve with American option have early exercise. Stock price $40, exercise price $50. This early example they are using X, not K. Risk-free rate is 10%. Sigma is 40%. Total time horizon is 5 months. The option is 5 months. So why I put a 0.4167? It's 5 divided by 12. Don't forget, we have 12 months per year. Now here, I'm going to ask you to do 5 steps. Each month, you do 0.0 month. The delta T is 1 over 12, equal to 0.0833. Using CRR model, first let's calculate U, which is e to the power of sigma times square root of delta T. Delta T here is a square root of 0.0833. You get 1.12224. Do an inverse. 1 divided by that, you get 0.089. Right? Now this is the alpha, the drift term, the alpha is 10%. Increase to 10%, but only for 1 month. So it's 1.0084. The probability is 0.5. Now, this is the parameter you have to calculate. In the final, I'm going to ask you to calculate the parameter by hand. Okay? Now, as a mechanic, how to do it? Pretty straightforward. This is from the derived gem. You put a 5 step. You say, well, let's do 5 steps. What the price is. They automatically come up with a model look like this. On the top is the forward-looking mapping for the underlying asset. Up, 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 5 steps. Underneath is the payoff of that put, out of money or in the money. Then go backwards, the backwardation induction. So the put value is 4.49. 4.49 put option. Now, if it's American option, you have to check on each interim node. You have to check what is the value of early exercise. In here, go up, go down, down, down. The third down, the fourth down. The early exercise price is 14.64. As a matter of fact, that one will give you the high value. Instead of looking at let it go alive, the red one indicates early exercise occur. It have high value. That value will be put into discount back to the value 4.49. Compare with early 4.49. This one have some value change. Right now, here is the essence of what approximation will help you. Remember, at first we do like 2 steps. One step is very simplistic. Let's assuming the true value of this option. Let's say it's $4.30. It's somewhere, Black-Scholes model give you $4.30. But if you do 2 steps, because it's too rough, the value is $4. Let's say 4 step value 4.7, 5 step value going down. So the oscillates. The approximation give you very rough idea, have big error. However, the magnitude of the error becomes smaller and smaller. See, if the step cut into very tiny one, like 30, 40, even 50, now it's close to 4.3. Now we will say the 50, that one we call it convergence. So usually we'll say that, oh, that's the difference. You can do 100. But if anything, the value is below 1 penny, we say it's converged, it's equal. So the precise, you don't need to be more precise than the 1 penny. So here it shows you the more step you put in, the accurate you get to the true value. Remember, the binomial tree itself is an approximation method. Now, this is very important. Now, I'm going to use the derivative, using the derivative to do this, to show you some example. The example I'm using, I want you to also repeat. Just look at your textbook, example chapter 13.4, Black-Scholes model, on page 305. You plug in the stock value. You were using equity. The is the equity value. Equity value. We put stock price 42, exercise price, let's say, strike price 40, right? 40, 42. Volatility 20%. Risk-free rate 10%. Now we do core value. Look at the core is highlighted. It's Black-Scholes model. The value is $4.76. Now, when you report to me just $4.76, you don't need to be so exact. $4.76 per share, okay, per call. Let's look at the right-hand side. It's a put. I highlight on the top put. Same thing. The Black-Scholes model is the value is 81 cents, 0.8085, 81 cents, 81 cents. Now let's assuming these two are the exact formula. Black-Scholes model basically the exact value. Now let's do a approximation with binomial model, the tree model. My next slide showed you the core value. Now remember the core value in Black-Scholes model is $4.76. Now this time we're going to use the European core. European call, but using binomial trade. So in the option type of option data here, you choose binomial European. And you also need to looking at the steps. I put a 5. I put a 5. You can put a 4, put a 5 will be good. I'm using 5. Now 5 is a rough estimate. The book said at least you need to put a 30 in, but I put a 5 in. So what the result is? The result is 4.74. See that? 4.75. Now let's try say that 4.70. It's pretty close. 4.76 is the true one. This one is $1 difference. One penny difference. 1 penny difference. Now let's move to the right-hand side. This time I'm put 100 repetition, 100 times steps. Very tiny, hours by hours. The result is 4.76. As a matter of fact, this one actually have smaller. Now, by the way, depending on how many time steps, it never totally exact, particularly if you're looking at it to be more accurate, like a 4-digit after decimal point. The point I want to make is the tree steps, smaller tree step, single digit, sometimes is not too accurate. You have to go improve to I usually put a $100 tree step in it because the computer do those mechanic for you. Okay, so this one show you. Later I'll using derivative show you more. Now let's look at European American options. Now Black-Scholes model will not allow us to do American option. They only for European only exercise the maturity. Now this time on the left is a European option. So here is binomial European. So there is no early exercise for the put. The value is 81. It's pretty accurate. I put a 100 steps. So it's at 81 cents. American option. So option types binomial American, still 100, is 91. See that? 10 cents more because early exercise. So we will put it like the value is higher. Value is high. Now, binomial model in this sense, why practitioner won't use it? Because most options traded in the United States are American. So when I give you the first lecture on Black-Scholes model, I say it's a very important work. But however, its use in practice is very limited. As a matter of fact, people using Black-Scholes model usually go backwards to find the implied volatility. But using the CRR model, to Cox Ross-Rubinstein model to do the actual pricing, because all the American option are all the option in the United States, except like S&P 500 index future is European. Most American options are American. So early exercise are not. Now, in some kind of unusual situation, the CRR model might not working. It is when the volatility is too high. In other words, you might get a probability equal negative. In that case, because we know probability will never be negative, right? So in that case, you have to using this model instead of using the half. We're using probability of 0.5. Here's the model. In case you get the negative probability. Remember, then Black-Scholes model the CRR model failed. You're using the following formula to replace their model. I'm going to skip Monte Carlo. I'm going to skip Monte Carlo. That is not. We don't have the right time to do that. But I do want to add one more thing to this lecture, already lengthy. But actually, it's not that difficult. The binomial trade is not difficult. It's more conceptualized. It's exotic option to looking at the payoff is not traditional European or American. Derivative securities with more complicated payoff are called exotics. Most exotic options are traded over the counter. International finance worked on like a barrier model, etc. Very, very common, very common. And in exotic option, let me show you. I have a handout. You can click the insert, the embedded file to get those handout. Let me jump to the handout for exotic option. Okay, where's my handout here? Okay, here. Let me enlarge this a little bit. Exotic option. Now we do have a chapter for that, but we don't have time to do that. It's too lengthy. So I'll just give you some example. Those example we particularly are used in international trade. What is called the Asian option, or some called the average option. The Asian option, no, it's with the European option, American option. So people add another option. We call it Asian option. It's not really traded in Asian country, but Asian. But they just it's like funny words for that. The average option. Now let's look at payoff. For a core Asian option or average option, if you can see that, for core, let me enlarge it. For a core, its payoff is the maximum, the average stock price minus exercise price. The average stock price. In other words, they are not looking at what the spot price is. You're looking at how do you get there. That's a typical what we call path independent. This one is path dependent. In Black-Scholes model, it's path independent. How do you get there is irrelevant. Here, irrelevant. Is relevant. Now, then just a quick example looking at this kind of option, how that look like. Let me see this one. Okay, I already did this two steps, just show you the Asian option. Here is the core option on the left, 50, 75, 112, the up 50%, 50% up, 50% down, you're looking at. Now, how do I exercise for that? Exercise, looking at, with the exercise price, let's see, 50, is, instead of using the final price, 112.5, the average stock price, if you go up, is 50 plus 75 plus 112.5 divided by 3. So what is the average? You get up. The average 79.1667. So that is the average price minus 50. You get a 29. You see that? Okay. So how do you get there matters. In this situation, the particular contract require that. Now let's look at another one. Here is a look back option. Look back option is a European style option. The payoff for call is maximum ST at the last price minus the minimum S, the lowest stock price. You look back. It will allow you to look back. The most favorable term. Okay. Number 2, I also have example. It worked out. You can just take a look to see how the payoff is path dependent. The among the exotic option I want to emphasize is the barrier option, widely used in international transportation, as a matter of fact. A barrier option, they set a barrier price, or called a triggering price. When the stock hit, when the underlying asset hit this barrier, you either knock out, you don't have option. If you already have it, you don't have option. Or you knocked in, or you don't have option, but you have in option. Let's look at one example. Let's B be the barrier. Now let's look at down and out option for this Berry option. Now, this Berry option at the same price, they set up. Let's look at the up and out put, the last one. The barrier at 75. So you hit the barrier, there's no option. If you're below this barrier, then you have the option. So let's look at this. Now, if the put up and out put option with the barrier 75, with the value equal to 11.88, 11.8797, which is less than a plain vanilla European put. If there's no barrier, this option is 14.994. Do I have one? Oh, not this one. Yeah. Well, I calculate it. It's 14. If you try it, it's $14.94. In other words, a traditional European put has a value of 14.94. A up and out put only have 11.88. Why? Because it will never occur anything outside the barrier. You exclude certain payoff out of the contract. The why international trade, like shipping, transportation, have insurance. Sometimes those insurance will exclude God's act. For example, like a wind, fire, or whatever the condition, weather condition. The ship is sunk. Certain insurance won't cover that. In that case, the insurance premium will go down. That's why I want you to take a look at the barrier option to have a sense of if you exclude the payoff, then your premium will go down because it not covered the whole scenario. So in insurance, sometimes people exclude a certain event. In medical insurance, for example, certain things not included, the premium will go down drastically. All right, at the very end, this is pretty much of the binomial model. It's a useful concept you need to know. How do you program in it? You don't need to worry about it because this, I think, the programmer will do that. But you need to know what the basic idea is go forward, go backward. Before I go, let me show you the derivative. Okay, finally we will work on a derivative. I'm going to use the derivative using the 13.4 example. Stock price 42, exercise 40. Now let's look at the put version. The European version is 81 cents. Let's assuming this is exact value, 81 cents. Now let's change this to binomial model, CRR model, to European. I go to European. I put a step. I'll put a small step in. I'll put, let's say, 4 steps. I put 4 steps in. Hit in 4 steps. Oh, it's a put. Then I hit calculate. Now, it gives you the estimation or approximation of 47 cents, which is 6 cents more. Now, you also can look in there. If your step is less than 10, click display tree. See the display tree? Click this one. Display tree will automatically show you the, let me enlarge that, the payoff. Dismiss tree. So this is what the value is, 67 cents. On the top of each box is the underlying stock price. On the bottom of each box is the put value. Now the red one means exercise. It's a European option. You only can exercise when it's at maturity. So the 5 period, you get a maturity. right? This is European model. So the using the discount factor to find each node and go backwards, which is at the very beginning 0.087. Now let's look at back. This time I'm going to change this one into American option. The only thing is just change option type. American option. In American option, I'm still using 4, but assuming this, it might have a chance to have early exercise. Let me do that. When I click it, calculation to see the value jump to 93 or 94 cents. The reason it can be early exercised. Using the tree, since it's less than 10, American option, okay? See, the American option will be early exercise at the time period, 3 months. So you will not move to the another 3 months. You basically stop at the third step. You never go to the very end. You early exercise at the time 3 months from now, 0.25. You ignore all the future red. Those, how do you calculate? The value is 9. By the way, because I want to show you the chart, so those values are not very accurate. I'm using smaller steps, right? Now in order to do this, I usually put a 100 as a steps, right? So the computer does those things pretty quick. So I hit my 100. Now in 100, the calculation will give you, well, 91. That actually I consider is almost exact number, 91, right? Now you cannot using display tree because it says no, it's too many steps, right? Cannot using display tree. So 91. In this case, 91 is the American option for this call. Now Black-Scholes model cannot work on that because it will not allow you to the American option. So I want to play with this model and particularly using small steps to looking at it. Because they all do those things. You do once exercise, but let computer do the rest of it. But before you let computer do that, you need to understand what the behind the scene really is. So the option type about derivative, in addition to the traditional Black-Scholes binomial, also Asian option, barrier option, binary option. Binary option, the cash and the nothing. As a matter of fact, it's interesting. It's a gambling model. It's give you the chances. You play, Russian roulette or whatever the row. Give you chances to calculate what the probability, what the payoff should be. It's pretty interesting. The exotic option in it, and the choosy option, etc. Since we don't have a time to really do that, you can play around using those option model. I'm not sure if in the fundamental, it definitely in the original book, they have a chapter talking about the gambling model. How do you basically pricing those gambling games in casinos, right? All right. That's all. Play around this model and working on the exercise.